Welcome to Fragmented, an Android developer podcast where we talk about building good software and becoming better Android developers. I'm Donn Felker.
And I'm Kaushik Gopal.
Welcome to the show. This episode of Fragmented is brought to you by Rollbar. With Rollbar, you can detect, diagnose, and defeat errors. If you're not familiar with Rollbar, let me take you on a quick journey. Have you ever run into that situation where you need to track an error from your Android app all the way back to the server? Have you ever tried to do that manually? Yeah, it's not that fun. It's about as fun as shoveling 4 feet of snow. I did that this winter, actually. Shoveling 4 feet of snow kind of sucks. Anyway, tracing an error from the app to the server is difficult, and if you don't have the tools to do it, well, it's nearly impossible in some instances. Trust me, I've tried. With Rollbar, you can track errors on your app as well as through the server code as well. It's super simple to set up too. On average, it takes less than 8 minutes to set up in your app. Existing customers for Rollbar include Heroku, Twilio, Kayak, Instacart. Hey, Kaushik works there. Zendesk, Twitch, and many, many more. Go to rollbar.com/fragmented and you'll get the Bootstrap plan for free for 90 days. This includes 300,000 errors tracked for free. Now, I sure hope you don't have 300,000 errors happening in your app, but anyway, that's a lot of errors. Wow. Anyway, that's rollbar.com/fragmented. Okay, welcome back. Today we're going to talk about item number 9 in Joshua Bloch's Effective Java book. For those of you that have just joined us on our journey through the Effective Java book and here on the Fragmented podcast, just to let you know, we are walking through in these little mini fragment episodes. We are talking about Joshua Bloch's Effective Java book, and we're going through each of the items and discussing them in kind of some detail and how it applies to us as Java developers, kind of in an Android world, and apply any Android specifications or reasoning behind why it might be important. So let's go ahead and hop into number 9. Number 9 says, always override hashCode when you override equals. Now, this is basically a general contract for object.hashCode. So anytime you override equals method, you should be overriding the hashCode as well. And failure to do so is basically a violation of the general contract of object.hashCode. And it basically prevents your class from functioning properly in conjunction with all hashed-based collections like hash map, hash set, hash table. So if you're using a hash map, a hash set, or hash table, and I pretty much guarantee that you are in your code somewhere, you need to make sure that you're overriding hashCode so you get the proper semantics involved with those different data structures. Now, there is a specification from Java Standard Edition 6 here that we'll talk about here. There's 3 items, and the first item basically says for the object.hashCode is it must consistently return the same integer if it's executed. You know, you have an object and you call get hashCode many times during the execution of your application, and it's the same object, it should return the same integer every single time. The second one is if 2 objects are equals according to the equals method, which we covered in item number 8. Remember, that was one of the previous episodes here. Item number 8 is a very in-depth talk about how to implement the equals method. So if 2 objects are equals according to the equals method, then calling the hashCode method on those 2 objects must produce the same integer result. So the hashCode method must return a integer of the same value. So if I have 2 person objects, they're both Donn Felker in both of them, and the equals method says, yep, both of these objects are equal to each other, then the hashCode method should return the same integer. So it should return an integer. We could just say +1 and that's good to go. Now it could be any integer. It could be 9,999, whatever. It doesn't matter. It just needs to return the same integer. Now the next one, the last one here, number 3, is a little bit confusing. And I'm going to read it as it's stated in the specification, and then we'll talk about it here in a second. The specification says, it is not required that if 2 objects are unequal according to the equals object method, then calling the hashCode method on each of the 2 objects must provide distinct integer results. However, the programmer should be aware that producing distinct integer results for unequal objects may improve the performance of hash tables. So basically it's saying, look, if the equals method has been overridden and the equals method determines that 2 objects are not equal, the specification says that, well, the hashCode doesn't have to be distinct. They don't have to be different, but you probably do want to make it distinct. You probably do want to make those integers different, because producing distinct integer results in those unequal objects will improve the performance of the hash tables and those types of data structures. So what we're really getting at here is that if you override the equals method and objects are considered equal, then the hash code must be implemented as well, and the integer values must match as well. So it must return equal values as well. So equals object must have equal hash code. Okay, now let's talk about an example here. Let's assume you've created an object that stores social security numbers, right? It's got the 3 digits, 2 digits, and 3 digits again, or excuse me, 4 digits at the end. You'll just call this social security number, and you want to put this in a map, and the map is going to have the key type is going to be the social security number, and the value will just be a string, and we'll call it a name. And so follow along if you can in the code, but you're going to want to take a look at the book just to get some understanding of where the error might happen. But let's assume we've implemented that. We've implemented the equals method, and the equals method just kind of checks to make sure that the beginning, the middle, and the end of the social security number are the same. And then it returns it. But for some reason, we forgot to implement the hash code. Happens all the time. We just forgot to do it. Now, what we're going to do is we're going to stuff this social security number inside of a hash map. So we say map social security number, comma, string, which is going to be the name, equals new hash map social security number, and comma, string is the type for the value. And then what I'm going to do is I want to put a new social security number inside of this map, and I'm going to say map.put new social security number, provide some digits, comma, the name, we'll say Donn, and then we close it out. So now I've put a new record inside of a new item in this hash map. And so we have one object and the value equates to Donn. Now, if at this point, if I were to say map.get, and of course map.get needs an object to be able to determine if it has that object in there, I'd pass in a new social security number instance. I'd say new social security number, and I pass in the same digits that I passed in before. So that being the same social security number, what would you expect would happen? Most likely you would expect the value that we returned would be Donn. Well, but it actually, in this case, is going to return null. And the reason why that it's going to return null is because one is used for insertion in the hash map, and the second one, the instance we're trying to use for retrieval, has failed to override a hash code. So the two equal instances have completely unequal hash codes. And so the hash map is saying, well, it treats these as different objects. So again, it's in violation of the hash code contract that we just talked about previously. So what's going to happen is the hash map is going to look for the social security number in a different hash bucket from the one that it was stored in by the original put method, even though the instances happen to be equal according to the equals method. Now, the hash map has an internal optimization that caches the hash code associated with each entry, and it doesn't bother checking for any object equality if the hash codes don't match. Make sense? So if we don't override hash codes, we stuff stuff into a map, we're not going to get the equality checking inside of a map that we've had before. And I can tell you what, I've ran into this problem many times, banged my head against the wall, like, why are my objects not coming out of the map? I am giving it the same one, it's not working. It's because I didn't override hashCode. And unfortunately, it was one of those things I didn't realize until I started Googling around and ran into it on Stack Overflow. So now fixing the problem is pretty easy. All we have to do is implement hashCode on the number class. Now, you could do this pretty easily. You can write a correct hashCode, very trivial one, but it's also could be very error prone. For example, you could just say, hey, hashCode return 42. Just return an integer. So you could do that. Quick side note, do you happen to know why you always see the number 42 everywhere? So just in case you haven't, the number 42 is in the Hitchhiker's Guide to the Galaxy by Douglas Adams. It's a book. It's a very popular book among sci-fi and tech crowd. And basically, it's the answer to the ultimate question of life, the universe, and everything. And it's calculated by this computer named Deep Thought, and it's supposedly been calculating it for millions of years and so forth. And basically, the answer to life and everything of in that nature is 42. So it's kind of like this internal joke when you see 42 in code. It's like someone's age, or the returning a value, or the price of something. It's kind of a throwback to the Hitchhiker's Guide to the Galaxy by Douglas Adams. So just a quick little tech tidbit there. So again, we're overriding the hash code. We're returning the number 42. Now, this is, it's legal, but it's one that you probably should never use. Now, it's legal because we're just returning an integer, and that's what we should be doing. But the problem with it is every single social security number object that we create is going to be equal to itself according to this hash code. So if we put them inside of a map, there will only be one inside that map because the hash code is going to see that there's already one in there with that hash code. So every object needs to have a different hash code to make sure that it's unique. So again, kind of following back to that contract. If the equals method says that an object is equal, then the hash code must also be equal. So, well, how do we implement a good hash code? That's a good question. Now, a good hash code usually produces unequal hash codes for unequal objects. Kind of self-explanatory, but this can kind of get kind of complicated over time because you have all these different fields and different rules and so forth. Now, it can be difficult to implement, but there is a simple recipe you can follow, and thankfully, Joshua has included one here in the book. So I'm going to kind of walk you through it here. It's kind of confusing because you're not looking at the code. You're just listening to me talk about code, which is really kind of meta. But anyway, what you need to do is store some constant non-zero value, say like 17 in a variable. Call it like result or whatever you want to call it. And then for each significant field that's inside of your object, and you should take that into account and decide what is significant versus non-significant by what you're using in the equals method. So if you're only using the social security number, you're only using those 3 fields, then you should only use probably those 3 fields to help calculate your hash code. You don't need to include something arbitrary, anything else. Now there's a couple steps here for each int value. Compute an int hash code for the code C for the field. So basically, if the field is a Boolean, you want to say if it's true, return a 1, otherwise return 0. If the field is a byte, char, short, or int, you want to just return the integer value. If it's a long, you're going to want to do a little bit shifting here and produce an integer value. If it's a float, you want to do float to int bits. You pass in the float value, and it'll give you the integer bits for that. If it's a double, you want to do double to long bits, and so forth. And then the resulting hash will be kind of a longer number. Now, if the field you're going to be using is an object reference, then you're going to want to use that class's equals methods and recursively start invoking the equals methods to calculate the hash code. Now, if there's a more complex comparison required, Joshua says you can compute a canonical representation for the field and invoke the hash code of the canonical representation. So, for example, if the value of the field is null, then return 0, or other constant, but 0 is type of traditional. Maybe the field is an array. You could treat each element as if it were a separate field. You could do that, and so forth. So there's a bunch of different options here. And then what you need to do is combine the hash code that was computed in the previous step into a result that follows. So, for example, take 31 times the result plus the original value, the calculated value of C, and that is going to be your calculated hash code that should be unique to each an individual object that does not equal each other. Now, so how do you know this works? Well, the best way, as usual, is to write unit tests to verify your intuition. So create a vast unit test suite around this to verify that if an object is equal, the hash code equals. If it's unequal, the hash codes are unequal, and make sure that that's the case. And if it's not, well, then at least you have some tests backing it up and you can figure it out until you get it right. Now, there are some caveats, of course. You want to maybe exclude some redundant fields from your hash code computation. So if the field can be calculated based upon other fields, then you can go ahead and ignore it. Maybe any non-zero fields you can go ahead and ignore as well, and so forth. One final thing here. When we talked about creating that final hash code and returning that result, there was something I had said in there. I said 31 times the result plus the computed value. Now, the multiplication that we did in that step makes the result depend on the order of certain fields. Now, that yields for a much better hash function and so forth. Now, but if the multiplication was omitted from this hash function, all anagrams would have an identical hash code, and the value 31 was chosen because it's an odd prime. And if it were even, the multiplication overflow, and if the multiplication overflowed, some information technically could be lost, as multiplication by 2 is equivalent to shifting bits. So the advantage to using the prime, of course, is a little less clear, but it is traditional. And a nice property of the value 31 is that the multiplication can be replaced by a shift and a subtraction for better performance. And so he outlines some code here, like 31 times I equals I shifting left to the 5 minus 1. So and he states here, modern virtual machines do this sort of optimization for you automatically. And so this is how you can kind of write a kind of robust hashcode algorithm. Another consideration to make is if for some reason calculating your hash code, it takes a significant amount of processing time, and this is something that you would want to measure. Don't be premature about it and try to optimize something if you know that it's not a bottleneck. you might want to consider caching your hash code instead of recalculating it each time that you do it. And on that same token, don't be tempted to exclude like certain significant parts of your object from the hash code just to improve performance because you think that, well, this is too slow. Just go ahead and cache it. It's not that big of a deal. You're gonna do it once, and if you want your maps to work correctly, this is something that you're gonna want to implement the first time correctly. And that pretty much wraps it up for item number 9 today. So just kind of recap here again from the top. Item number 9 is always override hash code when you override equals. And when you override equals, and if 2 objects are equal, then the hash code should be equal as well. So if 2 person objects, both called Donn Felker, are considered equal according to the equals method, then the hash code should return the same integer value. This hash code should be generated based upon significant fields inside of your model. And so it could be like the first name, the last name, social security number, all these significant fields should help you calculate your hash code. How do you find those significant fields? Take a look at your equals method. Anything that you're using inside of the equals method should probably be used for your hash code calculation. Then you need to walk through each of your different types of calculations. If they're, value types, you should be doing certain computations as stated inside of the Effective Java book. If they are references, you'll want to hop into the hash code implementations for those and possibly recursively walk the object graph to get the proper hash code for your application, if it is a significant field. If it's not, then don't worry about it. And that kind of covers the basics here. Now, there's a lot of code that's some bit shifting and stuff like that for item number 9. I highly recommend that you, again, get the book Effective Java. Some people think that it might be a little pricey. Hey, it's $30 or whatever the price might be at this time on Amazon. It ranges. A couple weeks ago, it was on sale for like $12. You can kind of throw a watch on it and see when the price goes down. But regardless, it's a small investment for the quality of the code that you're going to write in your career. And even if you save yourself 1 hour from preventing a bug, or you fix a bug because you bought the book, it immediately pays for itself, and everything else you're going to get out of it is going to be gravy. So definitely check out the book, Effective Java 2nd edition. So until next time, guys, thanks a lot. Once again, we'd like to thank our sponsor for this episode, Rollbar. With Rollbar, you get the context, insights, and control you need to find and fix bugs faster. Go to rollbar.com/fragmented to get the Bootstrap plan for free for 90 days. Again, that's rollbar.com/fragmented.